Hello, everybody, and today I'm going to walk you through my AppSec vulnerability management case study that I built. The goal of this lab was just to demonstrate the end-to-end AppSec VM lifecycle. So we're going from infrastructure deployment to application scanning, all the way to finding vulnerabilities, remediating them, and then recording our evidence as well. Throughout this lab, I'll go through my AppSec scanning tools, remediation evidence, and how it aligns with the secure software development lifecycle. The main thing I wanted to show here is not just the tools I'm using, but the process. How confirmed vulnerabilities move from detection, identification, all the way down to remediation and validation. So with that being said, let's go ahead and continue to the next slide for our architecture at a glance. And right here is just a high level overview of my lab architecture. The flows start from Terraform. I use Terraform to build out the Azure infrastructure. And this includes my Azure group, app service plan, and also the Linux web app that I used as well. From there, I took the app I built using Node, and I put it in the container using Docker. I hosted the container in Azure App Service. I use GitHub Actions for my CI/CD pipeline as well as running my security workflows too. The key point here was not just to launch an intentionally vulnerable app, but I wanted to showcase me deploying this into a real CI/CD pipeline so that we can scan it, validate it, capture evidence against a live environment. I'll go deeper into each part of the architecture as we move through the presentation as well. But now let's go. Now that we got everything established with our architecture, I'll try to quickly walk through this and get through it as quickly as I possibly can. And we'll talk about the technology stack for this project. And this slide just breaks down the technology stack into three different areas. We have infrastructure, we also have delivery, and security. For the infrastructure, I use Terraform and Azure App Service. The Terraform gives me a repeatable way to build the environment. And Azure App Services permits me to host my application into a continuous cloud environment. And for delivery, I use Node and Express for the application. I use Docker for container packaging and GitHub Actions for my CI/CD pipeline. For security, I use tools like CodeQL, Gitleaks, Dependabot, Trivy, Checkov, and OWASP. Each tool handles different tasks across the application, the dependencies, the container image, the infrastructure code, and the running application. The reason I grouped this way is because I wanted the project to feel like an actual AppSec workflow, not just a collection of tools, you know? Next, I'll explain the life cycle that ties all of these pieces together. And right here, this is the core life cycle of this lab right here. The flow is identify, validate, map, prioritize, assign, remediate, and retest. The life cycle is very similar to infrastructure exposure management. In exposure management, we usually apply that process to endpoints, servers, network, assets, scanner outputs, and CVEs. But in AppSec, the same process applies, but the assets are different. Now we're talking about applications, APIs, source codes, dependencies, secrets, containers, and also pipelines. So the logic is familiar. You find the issue, you confirm it's real, you map it to known risk category, prioritize it, assign it to the right owner, you fix it, and then retest it, and then finally move it to closure. So yeah, so that's pretty much the flow. Now I'll show you how this lab is built and deployed before we move into security testing portion of this, all right? This slide shows the build and deployment flow that we have here. At the infrastructure level, Terraform builds the Azure resources. This includes the resource group, app service plan, the Linux web app. Azure App Service is the runtime where the application is hosted. The application itself is built in Node and Express, as I mentioned before. and Docker is used to package the app as a container image. GitHub Action handles the CI/CD side. That means deployment and security workflows can run from the repository instead of everything being done manually. And this screenshot here just serves as my deployment evidence. It shows how the workflow actually runs, and also that my application deployment process is tied to an actual CI/CD pipeline. Once the app is deployed, the next step is security testing, as we mentioned before, and I'll just go over those steps as well. So this slide is the security testing coverage across the web app. I use CodeQL for my SAST or static application security testing. This tool scans my source code for vulnerabilities, insecure coding patterns, and potential data flow issues before the app is even deployed. I use Gitleaks for secret scanning. This tool detects hard-coded secrets or secret-like patterns in my repository. Essentially, hard-coded secrets are risky because they can expose tokens, keys, or credentials, passwords, things of that nature, directly from the source code, from the source control. So Gitleaks scan for that behavior during each commit. And Dependabot is used for our software composition analysis, or SCA, which monitors our third-party dependencies for known vulnerabilities or outdated packets. This is crucial because the modern applications rely heavily on external libraries. So if we can catch those vulnerabilities at this level, we can then in turn strengthen our security posture. Trivy is used for our container vulnerability scanning. It checks the container, including the base image and packages, for any known vulnerabilities. Checkov is used to scan Terraform code for any misconfigurations. Since this is infrastructure as code, Checkov can help identify risky cloud configuration patterns before they even get deployed. And lastly, we have OWASP for our dynamic application security testing, or DAST. Unlike SAST, it tests applications while it's running by interacting with it like an external user, helping identify vulnerabilities in the application's behavior, such as authentication issues, insecure configurations, and even input validation flaws as well. The key point is the lab doesn't rely on just a single tool. It generates security signals across code, secrets, dependencies, containers, infrastructure, and the running application. Now that we have our security coverage in place, I'll show you the application's risk that I'll show you the application risk that I intentionally built into the lab. This is for testing purposes, of course. All right, so this slide right here shows the intentionally vulnerable roots of this application. The first risk scenario is the broken access control. In short, broken access can be an application that allows access to something the user should not be able to have access to. In this example, our broken access is an insecure direct object reference, or IDOR vulnerability, where changing the identifier can expose another user's data. Here, the root ends in profile ID equals 1. In this scenario, just by simply changing the identifier from a 1 to a 2, as in the image on the right, a user can view another person's profile data without even logging into that account or passing any kind of authorization checks. The slide also shows 3 additional scenarios: a debug route that exposes internal application details, missing security headers that weaken browser protections, and orders API that returns more information than necessary. I won't go deeply into each of these examples here, but I'll use the orders API for a deeper analysis on the next slide. The goal is to show, is to show how an analyst identifies the risk, captures that evidence, and turns those findings into a remediation guidance. So let's go ahead and continue on to the next slide. All right, so this slide is focusing on the findings intake and ownership process. For this walkthrough, I'm using the ticket AF004, which is for an excessive API data exposure environment. And it's on the route of /API orders, or is backslash rather, :ID, and that's our route right there. So in this scenario, the finding is assigned to the ticket ID, which is AF-004. I mapped it to the root as the one I mentioned above. It's tied to OWASP top 10 for broken access, and it's assigned to the proper owner. In this case, the owner would be the API owner as assigned on the ticket because the issue is with the API response. So from the mapping standpoint, this falls under OWASP A01 under broken access control. It also maps to the CWE number 200 for exposing sensitive information. And AppSec findings are often linked to more than one framework because it gives teams better context to make reporting more consistent. The risk is that the API is oversharing data. The response includes internal only fields that are not required by the client. That increases the blast radius if the endpoint is ever exposed, accessed, or abused. The recommended fix is to minimize the response to only the required fields. The validation plan is to capture the before payload, apply the fix, capture the after payload, and confirm that the internal fields are no longer exposed. In the event of a real-life vulnerability such as this would be where the findings become more actionable. It is no longer just a scanner result or a note in the report. It becomes a ticket with ownership, risk, remediation guidance, and eventually validation. The full investigation for these findings is available on the GitHub page in the reports folder. So feel free to go ahead and check all of that. This is just a presentation. I don't want to go through all of the details, but I will briefly go through all of it. All right. And again, I'm using the ticket AF-004 as an end-to-end example here. So now I'll show you the before and after evidence for this remediation that we're discussing right now. All right, so this slide just shows us the remediation and validation proof for ticket AF-004. On the before side, the API response returned internal only fields. Those fields were not needed by the client and should not have been exposed in a public response. The remediation was to update the API response logic so it only returns the fields that are required. Things like the order ID, customer name, total, and items. The implementation evidence shows how the response was minimized in the code. You should be able to see that there. The test evidence is also important because it helps prevent the issue from coming back later. The tests validate the internal fields like the internal notes or the payment adjacent values are not included in the public response. It's been excluded. So here, the remediation layer flow, we have the before evidence, then we have the code fix, then we have the after evidence, and finally, we have the validation. This is exactly what we needed to bring the ticket to closure. So this would obviously be much stronger than some developer out there saying, hey, the problem was fixed. Here, we validated everything. We applied the fix, validated, and retested. All right, so after the code level validation, I also want to show the scan-based validation against the running application. So we'll go ahead and go over to the next slide to show that. And in this slide, this is the OWASP ZAP baseline validation scan. After remediation, I retested the running scan, so there was evidence that the updated version had been deployed and remained accessible. I do not make, well, you know what? I do want to make an important distinction here. The ZAP baseline scan mainly performs passive checks, so it is not the ideal tool for confirming that specific API data leakage issues has been fully remediated. In an enterprise environment, I would use something more comprehensive, like a DAS platform such as Black Duck, Continuous Dynamic, along with targeted API tests to verify that the sensitive fields are no longer returned. This is just a lab right here. So I use Zap baseline scan as a practical validation step to demonstrate how dynamic testing can be integrated into the CI/CD pipeline. The overall process remains the same though. You fix the issue, deploy the fix, retest the running application, you capture the evidence, and then make your closure decision. All right. So now I'll connect this workflow to how this would normally work when you get approval from change management, because that's the real process. So let's go ahead and move on to the next slide. All right, and this slide is going to connect this lab to the actual real enterprise workflow. In a production environment, there's usually separation of duties. The person implementing the fix should not be the same person independently validating the remediation. The process usually starts with triage. The AppSec or vulnerability management team confirms the finding, validates the risk, and identifies the proper owner. For the higher risk issue, a change request is usually submitted. That gives the service owner, engineering manager, and the change board visibility into the scope, timing, and rollback plan just in case anything goes awry. Once the change is approved, the assigned engineer or API owner implements the fix. After that, the vulnerability management or AppSec team performs an independent retest. That validation step is what confirms whether the fix is actually working. And once the fix is validated, the ticket can then be closed with all of your linked evidence. The final piece is the lessons learned here, which is awesome because it gives the next analyst, somebody like me, or the engineering team a faster path if a similar issue was to appear again at some point in the future. So from there, let's also map this naturally into the secure software development lifecycle. All right, so in this slide, this shows how the lab aligns with the secure software development lifecycle. In the design phase, I define the AppSec workflow, the risk triage method, and the OWASP mapping. In the build phase, Terraform creates the infrastructure and the application code is deployed. In the test phase, the lab runs the static application security testing, dynamic application security testing, our software composition analysis, our secret scanning, our container scanning, and even the infrastructure as code scanning as well. In the release phase, GitHub Actions handles the deployment or the CI/CD pipeline. And in the operation phase, the findings are triaged, assigned to the owners, remediated, and then validated with evidence. The broader mapping is documented in the repository, but with this slide, I wanted to keep the story practical. This was where my hands-on demonstration of how AppSec can fit into the software development lifecycle. So with that, I'll close this with the outcome of the lab and what I would probably more than likely improve next on this. All right, so to close this out, I hope I was clear in explaining how vulnerability management ties in directly with application security. In this summary, this is the Azure-hosted AppSec lab where it demonstrates CI/CD integration with security scanning, OWASP-based findings, categorizations, clear remediation tickets, before and after evidence, and also validation before closure. The workflow stays consistent throughout. We identify, we validate, we prioritize, we assign the ownership, we're remediating, and then we're retesting or verifying. Overall, this was just a controlled lab, but the process does reflect how I would approach real AppSec vulnerability management work. So in closing, that's the walkthrough right there. The main thing I wanted to demonstrate is that vulnerability management process, I definitely already understand that, and it also applies to applications as well, APIs, code, containers, infrastructure, and pipelines. The same process is there. Thank y'all guys for taking the time to listen to this. And I really appreciate y'all feedback. And let's discuss it. What are y'all guys building for your CI/CD pipelines? I want to grow in this area, and I love to connect with other people such as myself, other analysts out there such as myself that's on this path. Talk to y'all soon.